que has venido a escuchar. Y os agradecería, visto que es una cosa bastante informal, aunque voy a usar mi iPad con mi letra, que es horrible, que no tengáis reparos en preguntar y usaré la pizarra si es necesario. Entonces, como he dicho, este es un artículo que salió recientemente, la semana pasada, que nos hablamos, ¿sí? Con unos colaboradores españoles, un colaborador español, Carlos Valle, José Figueroa, que está en... no borré tu API. Bueno, sorry. Este es el número que ha aparecido. Y Giris es un estudiante de José. Entonces, a lo mejor, pues si nosotros no estáis acostumbrados o estáis acostumbrados, habéis oído hablar BMS como una realización de asymptotic symmetry en el null infinity. Pero lo que hoy os voy a decir no tiene...
En vista de que tenemos invitado la charla, ¿podrías hablar en inglés? Vale, ¿todos hablan inglés? ¿Todos tienen inglés?
Ok.
Gracias.
I was saying that BMS symmetry, BMS was invented as this asymptotic symmetry of flat spaces. Has been a lot of work. But and here I am not going to do anything with asymptotic symmetries. And the point is that if we have an algebra, like rotation, we can have different realizations of this algebra in terms of spins or in terms of differential operators or creation, annihilation, and so on. Therefore, here I'm going to present a realization of this BMS symmetry with something rather simple, that is considering the free Klein-Gordon equation. And we will see how the free Klein-Gordon equation that you all know, you will discover this infinite-dimensional symmetry. The plan of the talk, I don't know how much I will cover, in a sense, is not so important, is how we will introduce in the BMS algebra parameter. It will come in a natural way. I will show you that the Lorentz-Casimir is central in the construction of this lambda BMS algebra, that we could understand really the role of the Lorentz for creation this lambda BMS algebra. And after, what we will do is to write this lambda BMS algebra in terms of two-dimensional conformal field theories and OPs that probably hope most of you know. And I will present another realization, this time in terms of the Gauss system of an string. If I have time, I will comment about BMS, conformal BMS. Therefore, let me go ahead. And maybe a few words, I don't want to enter in all the details. Why is useful this BMS symmetry and an essential BMS symmetry are related to short theorems. If one is studying scattering with one of the external legs, one of the, for example, the photon is going to zero, appears some soft theorem. It's called the Weinberg-Paul, and it's Strominger has shown how these soft theorems are related to the BS symmetry. Related to that, to BS symmetry, there is this Carrorian physics, and because essentially Carolian conformal physics is BMS symmetries, and there are several applications, in particular for the flat space holography, and I don't comment in the other ones unless you want some explanation. Now, the point is Longhi and Materassi. Longhi was one of my supervisors already in '69. And with Materassi, that was with a student in '98, they considered the following thing. Let's consider, and this was done in 4 dimensions without super rotations, and Campeggio was a master student of us, and of Carlos Valle and myself, and we wrote some paper in 2017. And the essential point will be the following. We consider a matrix Klein-Gordon Lagrangian whose solution, whose equation of motion of that, and the solution is given by this thing here. And here we expand, and this you know well, we expand in terms of Planck wave. Results, let me comment that this Planck wave results to be eigenstates of the translational operators, of the translational operator. P mu going to I. Partial. Okay, later, if I have time, I will comment what it would happen if we change these basics here. And that's the volume element on the cone. And as also you have seen in your studies of quantum field theory, the A's and A bar or A dagger, this is at this level, if we are classical, this is Poisson bracket, it has this symplectic structure. And it results that the Poincare plus dilatation operators, you know that by the network theory, we can express our concept currents in terms of the essential tensor, energy momentum tensor, but that is expressed in terms of fields and the momenta that are the time derivative of the field. But if you plug this in the expression, it gives you, for example, for the Poincare generators, for the translations, you give this one here. We have A dagger away. I will use it different times, different names, but I'm referring to the same thing. And K, we are in 2 dimensions, and this will be this mu 0, 1 and 2, and this K0 is written, okay, it is essentially this omega K squared. And the rotations are given by this expression here. Again, the point is that we have here A dagger, A, and some here a differential operator of first order, here was 0 order. And if we consider the boost, that's the structure that we have. Here again appears the momenta. If we consider t equals 0, this will disappear. And again, the structure is that we have A dagger, A, and some differential operator. And for dilatations, of course, the same thing. Therefore, it's natural to consider the 0 operators, the first order operators, and this we take t equal to 0, and one can check that these objects give the bilateral. Notice that I didn't put the special conformal transformations, and will be a reason for that. Okay, and another in the same way that this verifies the Poincare algebra, you can check that with the A's and the daggers with the symplectic structure also is giving the Poincare algebra. Now, it's useful to introduce polar coordinates, and we introduce this omega or k0 is r, and we have this thing here, and we can construct the corresponding boosts. Here I have called V1, V2 with a hat, that essentially is what it's in here, and it has this one here. Okay? Now, now we are going to do the following thing. We could consider the Casimir of Lorentz, not Poincaré. Okay? We are doing Lorentz. And since we have that is given by this contraction of the mu nu, and here we have Bose square minus Bose square plus J square, only one component, and that it has, in terms of these polar coordinates, it has this differential form where no dependence on phi. In this representation, it results that there is a relation among this expression here and the dilatation operator that I have wrote before. Okay, now what do we do with that? The idea, okay, maybe I should explain the idea of Longhi. The idea of Longhi was the following. Can I find a generalization of the K mu in such a way that I construct infinite number of supertranslations? And the answer was yes, and he found things in a way I will present maybe in a more modern way, I would say, that probably we should understand more things like that. And at this point, maybe it's not clear to you, but what we ask ourselves is, this is a differential operator, C2, we have constructed up here. And we ask, what are the eigenfunctions of this equation, of this differential equation, with some value alpha that belongs to the reals. And, okay, here, therefore, in order to write this solution, we want to find the solution for how it's called, P and C, this, ¿cómo se llama? C, T, this T, and there's no dependence on phi. Therefore, the solutions are going to be a function of R by a generic function on the sphere on S1, and we expand in Fourier modes. And the solution is given, the general solution for any alpha is given by this equation here, where is R to the minus lambda. Here's the definition alpha. You can write it in terms of this form, and exponentially nf. And n belongs to the integrals, and lambda is real. And this has to do with, in a certain sense, appears natural on S1. If we were in 4 dimensions, we will have S2, and it will appear the spherical harmonics. Now, the point it is, what will Longhi realize that when this alpha was 2 in was 3 in 4 dimensions is d minus 1, he solved and construct the algebra. Here we are going to be a little bit more general. A question up to now? I mean, I summarize. Klein-Gordon field, Poincaré algebra, Casimir operator of Lorentz, and we look for solutions of this type. Now, it results that the action that the action of these differential operators on the eigenfunctions is given by this expression here, and here appears this lambda that is a parameter that has nothing to do with the cosmological constant. Therefore, we have here different, in principle, this will be an infinite dimensional representation. Okay. And this infinite dimensional representation here, I make some comments about it. When lambda, it is not an integer, is an infinite dimensional representation that is known in the representations of SO2, that's names as the complementary series. When we take that lambda is an integer, we find with minus lambda, we find that there is a subalgebra. For example, for lambda equal to -1, there is a subalgebra that is given by this thing here. And this essentially is a combination of the boost and non-Hermitian combination of, if you wish, boost and angular momentum. For lambda equal to 0, we have a trivial representation. And when we consider this thing can be bigger as we want, therefore we have an infinite representation, and always will contain, for lambda equal to -1, this Poincare algebra. Therefore, in a sense, BMS, okay, it is Lorentz, this will make the role of Lorentz. No, sorry. Lorentz are these generators here, and this will make the role of the momenta. Now, when lambda is equal to n, we have a singular behavior, and there are two infinite dimensional representations given by this one here. But we are going to concentrate mainly in this in the realization in this one with lambda negative, because if we do lambda negative, maybe you can see that this is in this negative. It means that this is singular, this is irregular. For going r to 0, this goes to 0, therefore there's no singularity. Instead, if lambda is positive here, we are going to have a singularity. But we are not going to consider much this one. Therefore, here's an important comment. Lorentz generators are of first order, with no zero order term. On the other hand, omega n is a zero order term. Therefore, when you have a commutator with a differential operator with another one, it subtracts 1 degree. Therefore, essentially, we could write, we have the action, we have this action here, of the B's, the differential operator on the zero order object, and it results that what I was saying, this is a first order with our zero term, and this is zero order, therefore the result is a zero order. Therefore, essentially, this is the action of the boost on that, and I write as a commutator. Therefore, okay, that's the thing that I wrote before, and I can add that the zero order commute on themselves. Therefore, naturally, what we have at this level B, the boost, the angular momenta, an infinite number of translations, because these are translations commute. Therefore, we have constructed an infinite dimensional representation, and it results that this algebra is a BMS algebra. And it's the BMS algebra, the standard one, with lambda is equal to -1. This is already in the literature. I didn't put reference here. Obviously, we are not the only ones that have done things of this type, but okay. Now, I noticed the following thing, that instead, if you consider the Casimir, is a second order operator acting in a zero order, it gives it is the action of this one and an extra piece coming from here. And that's the difference. That's the difference with respect to here. When we have a first order with zero order, it gives nearly this action here, the analogous of this action. Instead, when you have a second order, it gives that. And this object here, when lambda is negative, it has a generalization. I mean, if we consider this algebra here as the piece, and this as the piece, this is a generalization for lambda generic of a generalization of the Poincare algebra, where instead of having omega 0, omega 1, or -1, we go from omega n to omega -n. Okay. Some question? Good. Next thing, it is, okay, you see here, we have only Lorentz, because these are the three generators of Lorentz, and infinite number of translations. Question, can I generalize these three Lorentz transformations to an infinite number of Lorentz transformations? And the answer will be yes. In fact, what we will do is the following. We have seen, there are two things that I want to comment. The first is that the Lorentz generators, as I wrote in the first transparency, maybe if I go backwards, as you can see from here, these one here are first order, okay? Therefore, and we have seen the role that the Casimir of Lorentz at the second order helps us to construct an infinite number of super translations. Now, can we use the Casimir of Lorentz to create more than three Lorentz transformations? And the answer will be yes. How we will do it? I'll show you again that transparency. Okay, the first thing is that the Lorentz generators are first order and commute with the Casimir. By definition, the Casimir of Lorentz commute with all generators, therefore it commutes. Therefore, the idea will be, let's consider the most general one, a first order differential operator. Here are generic functions that depend on R and phi. We are in 2 dimensions. And there is derivative with respect to R, derivative with respect to phi. And we are going to impose, before we constructed, the point was that the Casimir was commuting with the Lorentz, but now we impose that this differential operator commutes with the Casimir of Lorentz, okay? And this, if you do the computation, you can find that this L it has this form. The R depend, there is a function C of phi and a function B of phi. Has disappeared the dependence of R here and R here. Simply, this is a computation set. If this commutes, Lorentz commutes, I impose that this one also commutes. Okay. But there is also another interesting thing, that the Lorentz generators are divergenceless. And this imposes essentially, you should require that the divergence of L is equal to 0, and this will give a further relation among phi and B, and therefore that's the question. But you see immediately from here that this phi, this is an arbitrary function, B of phi is arbitrary. Therefore, we will have an infinite number or super rotation or super Lorentz. On the other hand, maybe to make contact with some expressions known in the literature, it is that we take this function here, we expand in Fourier modes, and the form for these objects are this Ln, where n goes from minus infinity to infinity. Okay, therefore, we have enlarged through the use of the Casimir operator. We have enlarged the number of superrotations. Now the algebra, it is this one, L with Ln. This is the bit algebra. We know if you was here a piece with the center extension, that will be the Virasoro algebra. And that's the reason that in the plan of the talk I put the centerless bile, because okay, we have that no center extension here, and the action of Ln on this omega n is given by this one. For lambda equal to -1, that was known in the literature, in particular by, I think was introduced by Glenn Barnage and Tossar in 2011. And more generally, for a lambda negative, which is an new algebra that has this parameter. Good. Now, the point it is that we know that the massless Klein-Gordon field is not only invariant under Poincaré, but under conformal transformation. And the conformal transformation has the ordinary Poincaré ones, plus 1 that is dilatation, plus 4 that is special conformal transformation. For a reason that we will see before, we will now to enlarge. Before, I have written an expression for D. Remember D. D has this expression here. This is called the Euler operator. It counts the homogeneity of, and here is a factor of 1/2. Okay. Therefore, the point is, can we generalize this to an infinite number of dilatations? This group here is the Bayer group that is called. It is smaller, it's 11-dimensional. It is not the 15-dimensional in the 4-dimensional case as the conformal group. Now, therefore, let's see how, again, the Casimir of Lorentz is going to make a role. No, really, okay. The point will be the following. We consider the most general differential operator of first order, but this time including the function C. Remember that in the expression of D was a factor of 1/2. Therefore, in a sense, this is imposing that. At this point, if we impose that the omega n provides a representation, that it means that this dilatation on omega n produced being a representation, it means that d of omega n is give omega n with some alpha, And one can prove that these coefficients A, B, and C can be written in terms of some function. You see, there is no dependence on phi, therefore it's natural that we work with this exponential, and in a sense, this in mind that we have an S1, therefore A can be written in this form here, with arbitrary coefficient K1, here K2 with this form of the exponentials, and C with this K3. And alpha results to be this particular combination. Okay, therefore, if we call this m minus n, we call P, and we have this form. We have therefore an infinite number of dilatations. And now, if now we impose that the component Z of that coincides with the one that we had before and is given by this expression here, K1 is equal to 1, K2 is equal to 0, K3 equal to 1/2, and the form of the infinite number of dilatations, it goes like that. And you can compute, since we have the generators, written in terms of differential operators of first order or zero order, we can compute this algebra. And that algebra is known as lambda BMS algebra, with lambda minus 1 that we have found before in our analysis. Also, people from Chile, by the way, Ricardo Troncoso, I remember him, some other persons also found this algebra. Now, the point you could ask yourself, why we don't try to do the same thing for the special conformal transformation? Can we construct an infinite number of a special conformal transformation? And we will see that there is a difficulty here. This is an open problem, therefore, if some of you have some idea, maybe you can contribute to that. And the point, essentially, there are several indications that makes the thing difficult to that you can generalize. You can check from the conformal algebra that you can construct from the Klein-Gordon field. In the same way, we will have the structure of all these operators is the following. All the operators that we construct are O equal to integral on the cone, A dagger, K, an operator, differential operator O, A. That simply could be an exercise, maybe of an exam of quantum field theory. Find the representation of the conformal group with the Klein-Gordon, the matrix Klein-Gordon field. And you will find that all the generators will be of this form. And by the way, the algebra of those operators in general results to be the algebra can be proved in our papers in the appendix, or 1 or 2. Is this thing here. The point that it makes different the special conformal transformation is that this one for the special conformal, independently of trying to extend, these are second order. And the special expression is given of this of yes, I have correctly. Are these second order differential operators. Now, another thing that Okay, therefore the first thing is that we pass from first order and zero order to second order. You know also, probably you should know, that the conformal algebra has two sub-Poincaré algebras. The conformal algebra has two subalgebras that are given by two Poincarés that are M mu nu and P mu. That is one Poincaré. But there is another Poincaré that are related by some automorphism that is done with M mu nu and K mu and K mu. Okay. Therefore, in a way, what we have done in this construction is that we manage to extend this to infinite supertranslation. Therefore, it will seem natural that you will like to see if I can extend these guys to an infinite set. By the way, these infinite ones commute among themselves. In our case, in 3 dimensions, that are parameterized with an integer PL prime commutes. Okay, if you try to do this, for this case, you are unable. You will find that KL, and this time you should, again, you will play with the Casimir operator, and you will find that certain KL, but this will not commute. Therefore, these are not candidates to be super translations. Therefore, it's clear, okay, that's an intuition, it's not a proof. There is no theorem on that. But since in order to create the conformal one, it is missing the D. And in particular, we should mix. In particular, we should mix P mu with K nu. Therefore, it's clear that this can be done at finite level, at finite algebra, 15-dimensional finite algebra in 4 dimensions. But we could not do it. In fact, this is telling we know that the case will commute. And this is not happening. Therefore, what should we do? I don't know. And I say that that's another problem for me and for the, for example, Ricardo Troncoso, as I will comment, and collaborators. I don't remember all the people, but I remember Ricardo. Well, found that a possibility of solving that is creating what is called a doubly algebra that I will comment later. It's not a Lie algebra. A doubly algebra is such that when you make the commutation, when we have a Lie algebra, we have something of the form Gij equal to some structure constant Jk. Okay, that's a Lie algebra. But a doubly algebra is when this guy is not a constant, not constant, and it depends non-linearly on the generators. For double algebras are non-linear algebras. Okay, therefore, let's move on. I don't have much to say. Yes, I don't have much to say about the canonical realization. We have found a realization in terms of, in a sense, of a free theory, in a free in momentum space. BMS has nothing to do. I mean, it's not linked to be an asymptotic symmetry. We have constructed a realization, and I'll show you another one. Other thing that we have done in our paper is to see, can we extend the algebra? Probably, maybe this you know. that if we consider the Galilei algebra, for example, we have that boost with momenta at the level of Galilei commutes. But you know, on the other hand, this will be Galilei. But on the other hand, doing some cohomology calculations or doing more trivial things, you can realize that this algebra can be extended with a central element that it results to be the, for example, the mass. I call Z. If I have a realization with a particle, the result of this is equal to m, the mass of a non-relativistic particle. Therefore, the question, the algebra, this lambda BMS algebra that we have constructed has no central extension. Therefore, it's natural to us, can we construct central extensions in a similar way to that? As we know from the DeWitt algebra, with the Ln, we know that there is a Virasoro algebra that has a central element, okay? That related to the central charge of the conformal algebra. And this can be done using cohomology. My colleagues, Jose Figueroa and Guidis are, why are you doing that? Are spacing cohomology, and one can do the following thing, can compute what are the extensions computed in the second cohomology class of Eilenberg-Chevrolet. And one is finding that there's a central extension in the commutator of L with L, and that's what probably you know from the Virasoro algebra. There is an extra one coming from L and dilatations, and here's another central extension, and there is a third one coming from the dilatation with itself. I mean, that's some mathematical well-defined problem. There are no more, there are three, and that's it. Now, given these three results, do we have some more down-to-earth pedestrian things? And maybe the answer is yes, if we know about two-dimensional conformal field theory and OPs. And now, let me, in a sense, rewrite the whole algebra in terms of, even with the central extensions, in terms of OPs. And that goes in the following way. We introduce three conformal fields in 2 dimensions. One with modes Ln and charge 2. D is one conformal field, n goes from minus infinity to infinity with weight -1, and the p's that are related to translation has weight 1 minus lambda. With lambda is equal to -1 coincides with this thing here. Now, if one has this field here, and one imposes associativity, and there is a very nice pack for computing operator power expansions by Tielemans, that was a student of Kwame Proyen in Leuven, that it computes the operator power expansions. For example, one of the fundamental requests is that you should have associativity. Therefore, without knowing which is the exact form of this one, when we have a realization, for example, of the strings, we know that T is derivative respect to X, derivative respect to X. But that's not the case here. This is more general, and that's a structure. And let me comment, if we're able to do that, there is, you see, there are pieces here that has T's. These mean regular, that these are not going to contribute to the commutation relation, because later, I will comment in a moment, how from the operator product expansion we can go to the commutators. That maybe you have done in some course. But the point is that here, this is weight 2, this is weight 2, and this is giving, therefore, 1 c to the 4, and here there is a number. And the fact that there is this number, it means that there is a central extension. When we do T with D, that was one that had a central extension, we have again 2 and 1 equals 3, and this is giving the coefficient here is a number, therefore we have a central extension. Instead, in this one here, we have 3 in different way. We have 2 plus 1, 3. For example, and that's in a certain sense new, when you do T with respect to P, there is no central extension here. For those of you that maybe you know the BMS 3 in particular, without dilatation, you will see that here it will appear some central extension, but then in the moment that we introduce this D, this is eaten and disappears. Instead, it appears a new one coming on D. This will be 1 and 1, 2, that is these 2 here, and here is the number. And that therefore is the 3 central extensions that we have. There is a technique, I don't have time to go into the details, but there is a technique that you can write, essentially, is this one, for example, is in the thesis of this guy, but I'm sure for the case of LN you have done yourself, how you can compute the commutator of modes in terms of the coefficient of the singular terms that appear on the OP. I am not going to enter that, it can be done. Therefore, now, let's go and let's see how we can have another realization of this lambda BMS algebra. And therefore, the point would be the following. Imagine we have a W BMS string where we don't know, it's not necessary to know what is a matter part, but we introduce the Gauss BC. Probably, I hope you have seen before the BC system in string theory, and we introduce 3 copies of BC, and the conformal weights are 2 minus 1, 1, 0, 1 minus lambda, lambda. That's a general rule of the BC system. And it results that the operator product expansion is given by this object here. And also, if you remember from string theory, you can compute what is the energy momentum tensor of the Gauss that we write here in terms of this B and C, that for lambda equal to -1 is the ordinary thing. But that's the way that you can compute. We know that we have central, why we have critical dimension 26. But when we put the Gauss is 0, therefore the Gauss, the conformal weight of the Gauss, it cancels when D is equal to 26, when you consider a generic D, and this one here for the ordinary one, it leaves that D to be equal to 26. Here I can construct my dilatations in terms of this Gauss system. There are 3 types of BC, and the corresponding P is given by that, and the central charges are given by these objects here in terms of this lambda operator. Therefore, it results that this energy momentum tensor with the Gauss, the dilatation with the Gauss, and the momentum with the Gauss obeys the lambda BMS algebra. Therefore, we have another realization. For those of you that are more familiar with conformal field theory, one also can construct the BRS current such that its square is equal to 0, that it's the reflection that K squared BRST is equal to 0, and it results that you can do this construction. I'm not going to give too many details on that. And let me jump, and here is the expression that we have is C1 with, in a sense, the constraint that is the energy momentum, C2 with the other constraint that are the dilatation of C3, and that are the other objects. And it results that J1 is a total derivative. And I think I will stop in doing that, and let me maybe in the 5 minutes that I have say a few things. 10 minutes. 10 minutes? Okay. Therefore, I will finish, and maybe after you would like to ask me some questions. Maybe I went too fast, but okay, this is what I have prepared. Sorry, you have lost, but you didn't ask me anything, therefore I didn't stop. And that is the paper that I was saying. That what about if we want really to include infinite number of special conformal transformations? I gave you some intuitive idea that that will be difficult. And these persons, I think that all of them are Chilean. Oscar Fuentealba, that now it is in Iquique. Hector González, I don't know where it is now. Alfredo Pérez is in the Sex and San Sebastián. David Tempo is in Iquique, and Ricardo Troncoso is in the Sex and San Sebastián. They realized that they could construct a W algebra. I explained you W algebra means that here some quadratic things, but they did at a classical level. And okay, again, playing with this operator for expansion, we introduce some extra field K that if we come in here also have weight 2. And we want to close that in such a way that is associative and is an algebra. This time will be a quantum W algebra, not a classical one that was in here. And you could do that. And for example, I don't put all the terms, but I want to, for example, in this term, when you do K with P, this is given by power 2, is given by this expression here, where you see the important thing is here. Let me comment on this point, that we have quadratic operator, therefore we don't have the algebra. Therefore, there is this property that was written in our paper, that there is not a way that can we introduce a current, a biaristic current in this situation. And essentially, that's it. Therefore, maybe I should conclude with some words, and maybe summarizing to make things simpler. What we have seen is that BMS symmetry that was discovered as an asymptotic symmetry for flat spaces is a realization, but the algebra has other realizations, some of them that even written in terms of free fields, or if you wish, in configuration space, or that we were working in momentum space. Therefore, in free momentum space, we can construct BMS. Can be done also in configuration space. I was in a school in Iquique, and Oscar Fuentealba gave a seminar, and he showed how in Minkowski you can, that is in a sense kinematic, one can get also this BMS transformation. Therefore, we can liberate ourselves of thinking that BMS is related to asymptotic symmetries, and that maybe is one of the lessons of the seminar, maybe the second lesson, not without a deep understanding, is how important it is the Casimir of Lorentz for the construction of the super translation, super rotation, super dilatation. And there are difficulties with the special conformal transformations that we don't know. And finally, it's clear that one can understand, one can generalize this to other field theories. Okay, field theories that are, for example, free. We can understand, first of all, finding the Poincaré algebra in terms of these fields. Before you were telling me about this Fields-Pauli. For example, in principle, we could find the solution in terms of plane wave. Therefore, in principle, we should be able to find some phi, and one could make a generalization. The form of Poincaré could be different, and probably could be also done what I have said just now for the case of IC, because there we have also some solution free. I mean, not putting gravity or simply free. Seeing can we find a solution in terms of operator, creation annihilation operator, and putting some eigenfunctions and span. I don't know, this already has been done. In the case of a scalar field, it coincides the IC for the scalar field with what I have done here. Therefore, one will need to consider some other field that is the image. And maybe I will finish with the following thing that now I'm talking about this, that what about if we choose a different basis for our eigenfunctions? And if you choose, and that has been proven in the literature, there is a very nice review by Laura Donate and another person that now I cannot remember in physics reports, where one realized that if one chooses eigenfunctions, the eigenfunctions of the Bush operator in one direction, that's in a natural way, plus Mellin transform, plus maybe a parameterization of the momenta is to celestial holography and conformal theory. Therefore, okay, there is something maybe to be useful. Maybe I finish here. I don't know how I did with time. Okay, therefore, it's done.
Thank you for this talk. Now we have some time for questions. Are there any questions?
Please.
You did this construction in 3 dimensions, right?
Yes.
Are there any problems when you go to 4 dimensions?
Okay, very good. For the canonical approach with the Casimir operator is a technical problem, because instead of having powers R2L and a function of R1, you will have hypergeometric functions. Therefore, you will start having some difficulty with this time. If you go higher, you will have even more problems. If you want to do it from the point of view of operator product expansions, Jose was telling me that there is a formation of the Japanese that can be done also in 4 dimensions, but that is more difficult than some vertex algebras that you could do it. But technically, it's a question that you will need to know more about special functions. But no conceptual block. I mean, for some discussion from the point of view of asymptotic symmetries, what sort of asymptotic symmetries should I, what sort of boundary conditions I should put in such a way for having a BMS in higher dimensions has been maybe some different results. For example, from the point of view of short theory, you can have short theory in higher dimensions, but from the point of view of symptomatic symmetries, that I am not very familiar with that, therefore maybe I'm not saying completely 100% things. I don't know the status now of what it is, but from this point of view that I'm saying, that doesn't count the dimension at all. It's only technical one instead of powers of fields. You will have more complicated special powers.
Any other questions?
I have a couple of related questions. First, about the simple example that you told us about the Galilean algebra. So,
Yes.
but of course, I know that there exists a Galilean algebra, but I have never seen the details. So, I was thinking of that. And the first case is that in the case that the Galileans are commuting the keys,
Yes.
because we have the empty space. And the other one, the other term, the central extension is arising because of the particle of mass m is breaking the symmetry. Is that simple as that?
No, it's not breaking the symmetry in a sense. The extra charge has to do with the number of particles more in general. You have the number of particles, this is the charge that counts how many particles you have. No, I don't think there is a breaking of the symmetry. And let me say now that you said that, with one of my students, we have constructed non-relativistic BMS doing the contraction of the Poincare BMS. Not the in that time I didn't know about the lambda BMS, therefore it could be done. And also it has been studied Carolian contractions of BMS. But I don't think but maybe why having the mass it will break the symmetry. Why do you think so?
No, I just was thinking that that was like we are putting a particle on top of the empty space, so that particle is going to break the translation or something.
Not that, because really we work in instead of working in 4 dimensions, we work in 5 dimensions. Because you see, there is also a curious phenomenon, maybe related to that, that is the Barman that would be the one with central extension in D dimensions is a subgroup of the Poincare in D+1. And here maybe you will have the time t and x, and here you will have an extra time. You will have other variable. I mean, here we will have t and by the way, you know that the invariance of the Rolling equation implies that the wave function is should transform non-trivially is a projective transformation. Essentially, it's Vx plus or minus, I don't remember, V squared over T, if psi of x. I mean, and that one is related to one of the coordinates of this extra one. Okay, I mean, something like that. Then, if I one vector field passes with respect to x and you look for the generators that commute with that, that's a way of getting the Barman algebra. I don't know. I don't think it is any breaking. It's maybe enlarging the space, but not breaking of proximity.
Más preguntas. So we thank again Professor Gomis. Talking right outside, you can also.